Good morning. Today we are going to present some methodologies and tools for assessing the role of renewables, especially PV and wind in the energy transition.
A key driver for the energy transition is climate change. The concentration of CO2 in the atmosphere continues to increase, and this is driven by the burning of fossil fuels. In fact, more than 80% of the total primary energy supply is still provided by fossil fuels. Air pollution is another key driver for the energy transition, as the energy sector is responsible for the largest part of air emissions, and in particular more than 90% of SO2, NOx and CO emissions. These have large negative impacts on the health and well-being of people around the world. Depletion of fossil fuels is another key reason why we need a fundamental transition in the energy system. These resources will not last forever, and it's currently being estimated that we have about 50 years worth of oil and gas resources based on the current production rate. Okay, so with the energy transition, it really revolves around decarbonizing the energy supply. And with that, we need to have a shift in the mix away from fossil fuels towards renewable energy resources. And this could include hydro, solar, wind, geothermal, biomass, and tidal. Of course, there are other potential contributors to the energy supply in a carbon-free world as well, like nuclear power. However, those resources are oftentimes more expensive than other solutions. At the global level, there is some fundamental factors that drive this energy transition. There are agreements like the Paris Agreement, which set the goal of avoiding an increase in the temperature to well below 2 degrees Celsius compared to pre-industrial levels. Okay, but it's important to recognize that renewables alone is not the full solution. We need strong transmission systems to transmit electricity from the point of production to end users, and we need to electrify a wide range of sectors out there in order to reach these ambitious decarbonization goals. Also, a key aspect of many of the renewable energy resources is that they are variable and uncertain. And to address that, we need more flexibility in the energy system. And a key solution towards that end is energy storage. We need that to ensure in the very short term power quality in the power grid. We need that for frequency regulation and other services to maintain reliability and stability in the grid. And also in the longer term, we need to shift energy between hours, days and sometimes seasons to ensure that we can deliver the needed electricity supply across the time horizons here. So another aspect is that electricity needs to have to communicate with other energy commodities. So we need cross-coupling and cross-vector interplay between electricity, hydrogen, gas and other commodities out there. In order to analyze these very challenging questions, it's important that we have the planning tools that we need to look at this from different perspectives, and we need to apply the best tools out there to analyze these important questions for the future energy supply.
As mentioned before, the rest has to be considered into a wider perspective. That is what we call electricity triangle. Power generation is one of the vertex of the triangle and is characterized by the generation directly as electricity, avoiding fossil fuel-fired power plants. The second vertex is the vertex of the energy vector, in which electricity is used for transmission and distribution of energy. The last vertex is the final uses. So in the final uses of energy, we resort mainly to electricity, in which we apply electricity for the residential, the transport and the industrial sectors as well. The implementation of the electricity triangle can follow two different paradigms. Supergrids, global in scale, with ultra-high voltage transmission systems, and concentrated high-rated power generation from renewables, and microgrids, local scale, based on distributed generation and distribution electricity systems.
PV generation and wind turbines are today the most used technologies in the world. Why? As told by my colleague Professor Bompard, solar energy is so huge that there is no concern about the consumption of future generations. The energy return on investment of PV and wind power is very good and, above all, increasing instead of that of fossil fuels. The Earth's crust is so rich of silicon that no scarcity of raw material is possible. The structure of the device is so compact and the thermal loading is so low that maintenance is not an issue. For these four reasons, the levelized cost of energy in many countries is the lowest one with respect to the other technologies. Just an example to clarify the vast potential of solar energy in a sunny country like Algeria, where a small square in the map is sufficient for meeting the consumption, and the capacity factor of sun-tracker PV system can approach 30%. The planning of installations for PV and wind power is subject to environmental constraints in both urban areas and remote zones. Thus, the appropriate software is a user-friendly platform that incorporates geomatics information and techno-economic parameters. The photovoltaic conversion is electrically modeled by an equivalent circuit and its parameters, depending on solar irradiance and cell temperature, to trace the IV curve in whatever conditions. The planning of PV power requires a straightforward model, including different types of losses in the energy conversion. The wind power is a cubic function of wind speed, which depends on the altitude with respect to the terrain, and its roughness may increase the turbulence, decreasing the wind turbine performance. From the manufacturer power curve of a wind turbine, it is possible to match its efficiency curve and the histogram of wind speed distribution in the selected site. A site, to be appropriate, must warrant high energy productivity, and so the PV systems are equipped either with one-axis sun trackers, if in remote areas, or are in building integration in urban areas. A site, to be appropriate, must warrant high energy productivity, and so the PV systems are equipped either with one-axis sun trackers, if in remote areas, or are in building integration in urban areas. Low maintenance costs are assured if the constraints about the slope of terrain, the altitude of the site, and the absence of sandstorms are imposed for wind turbines and PV modules. Cost effectiveness of the investments is assessed by net present value, internal rate of return, levelized cost of electricity indicators.
Uncertainty in renewable energy sources and their year-to-year variations can substantially change the generation expansion results. Energy storage deployment also plays an important role in the system's investment and operation and their associated costs. I'm going to briefly discuss the impacts of these factors on generation expansion problem. The objective in generation expansion problem is to minimize the total expected cost, including generation technologies, investment and operational costs in different years, and also energy storage costs, load curtailment costs, and reserves costs. This objective function is subject to different groups of constraints, such as technology-related constraints and system-level constraints. The key challenge in this problem is to account for the renewables uncertainty and their variation from year to year, and also account for renewables forecast uncertainty in reserve requirements, and also adequately represent flexibility characteristics of generation, demand, and energy storage. Here we want to show how important it is to base the planning decisions on multiple years of renewables data, and what happens if single year data is used in planning decisions. Our results show that basing expansion decision on some years, such as 2009 and 2010 in this data set, yields to very high operational costs in other years due to resource inadequacy. So to find a robust solution on the capacity expansion problem, we suggest to consider multiple years of variable renewable energy and load data in the optimization. Another important dimension in the generation expansion problem is the role of energy storage and how its added value change with installed capacity and duration. We observed that energy storage with higher energy capacities lead to more decrease in the system costs. However, its added value does not increase linearly with its installed capacity. And also our results indicate that short duration storage have the most significant impacts on the system configuration and cost, leading to higher break-even costs.
We developed a web-based platform for the planning of renewable energy sources in the Mediterranean area.
The platform gathers various data from public data sources through intelligent data gathering technologies, and after processing them, the data are stored into a database. The calculation kernel retrieves the data and call the function libraries to address the user questions to the web interface. The final results can be mapped for visualization, data tables for detailed analysis, or modules for computational narrative, in such a way to provide more customized output. The needed data comes from various sources. Thus is needed to clean the data, to validate and check for consistency before sending to the database. The geographical area considered in the platform involves 32 countries with around 10 terabytes of raw data, and in the example we were going to see, we show 3 countries with about 2 terabytes of data stored.
This is a demo of the REST platform. In the interactive map, some countries of the North Africa are selected to better show the main functions. It is possible to select different geographical levels. The map shows the results of the installation criteria. It is possible to select the most advisable sites for the REST plants. The colors show the productivity of the selected territories. The analysis can be applied for different technologies, and different configurations are available for further analysis. The mathematical models for the calculation of PV and wind plants production are implemented in the platform. The user can easily change the inputs and perform parametric analysis by creating and comparing case studies. The output of the platform are power profiles and financial and environmental results. In this view, you can see power profiles from a single-axis PV generator installed in a site in Algeria. Data are available in graph, charts, and they can also be exported for other analysis.
The platform has been used for developing a case study on the exploitation of renewable energy sources in North Africa through a scenario analysis by 2040. The considered scenarios have been built by combining 2 scenarios on renewables productivity and 2 scenarios for the energy demand in the North African countries. In particular, 3 productivity scenarios have been set. The first one only ensuring the fulfillment of the electricity demand of North Africa, while the other 2 allowing for a surplus of electricity available for export toward Europe. The total installed power of PV and wind installation in North Africa in the 3 scenarios ranges between 170 and 700 gigawatt. Regarding the demand projection, 2 scenarios have been implemented. A reference scenario projecting the total final energy consumption and electricity consumption based on the best fit of historical data, and then high electrification scenario using the same approach for total final consumption projection, but making the hypothesis of a 50% rate of electrification in all the countries. The forecasted growth of annual electricity consumption in the whole area is equal to around 60% with reference to the year 2017. Combining the 3 productivity scenarios and the 2 demand scenarios, 3 overall scenarios have been set. In 2 of them, a considerable annual surplus that can be exported to foreign countries is generated. In particular, more than 200 terawatt-hours for scenario B and about 420 terawatt-hours for scenario C. For investigating the possibility of exporting the produced surplus of electricity toward Europe, all the electricity infrastructure that could be built across the Mediterranean have been mapped. With respect to the current situation, characterized by 10 lines in operation for a total capacity of 5 gigawatt, the new interconnection are expected to provide additional 20 gigawatt of power with an investment of around 21 billion euros. The results we got show that only about 90 terawatt-hours per year, that is just a fraction of the available surplus, can be effectively exported towards Europe, covering just about 2.5% of the total European electricity demand, mainly due to the limited overall capacity of the infrastructures connected in North Africa and Europe, for a value of around 12 gigawatt. However, in a market perspective, the import of renewable electricity from North Africa could lead to a reduction in the European electricity price, thus resulting in economic savings, and also they can have positive effects in terms of environmental sustainability.
Okay, so to conclude, we argue that electricity, because it is the most effective way of delivering renewables, will be at the center of the energy transition. However, renewables on their own is not the entire solution. We need to develop the supporting infrastructure, and we need to electrify a number of energy sectors to reach these decarbonization goals. The energy transition is multidimensional and highly complex, and we need science-based supporting methods and tools to make the best possible decisions, considering all the impacts in a holistic way.
The RES planning needs to consider various information, from geometric data to technical features of the installation, for allowing the definition, implementation and comparison of alternative scenarios in order to identify the best solutions. The developed tools have to provide customized answers to the instances of several stakeholders, institutional and regulatory bodies, energy companies, financial investors, integrating different possible impact analysis in a multi-layer perspective. And this is the conceptual approach we used for RESPLAT. With reference to the proposed case study, exploitation of renewable energy sources in North Africa can easily allow to fulfill the internal electricity demand, even in the case of high electrification rates, making possible also a trade with Europe. Investment in infrastructures are crucial for building an effective energy dialogue based on RES between North Africa and Europe.